Okay, so today I'll talk about a very basic lattice-based signature scheme. So before that, I'll introduce a central notion in signature scheme, which is a trapdoor function. So a trapdoor function is defined from the domain X to a range Y. And the first requirement is it is one-way. So given Y in its domain, it's hard to find X such that X is its prime image. This is also called a one-way function. So a trapdoor function is always a one-way function. And second requirement is if you have a trapdoor, say there exists a trapdoor such that if you have this trapdoor, it's actually easy to find its prime image. There is this trapdoor and an efficient algorithm that's called F inverse, such that given this trapdoor information and Y, it's easy to find its pre-image X, where fx equal to Y. So in the ISA-based signature, recall that our trapdoor function is defined to be and the trapdoor is n. Where okay, now, and this trapdoor is defined based on a number theoretic assumption. Now we need a trapdoor that's from a lattice-based assumption.
Could you explain what's TD, what's N, YX?
Oh, if you are not familiar with ISA, it's okay. Just draw some connection here.
Yeah. So the exponent of X should be.
Oh, this is E. Yeah. Recall that in lattice-based assumption, we have a very natural one-way function, which is you are given a matrix A and the X is a small vector. Simply outputs A times X. And this is one way from the shortest integer solution. I think that was presented by some guy last week. So this is actually one way. So the first requirement is satisfied. And now we need to find a trapdoor such that, let's denote this by Y. So firstly, this X is not unique. I want to emphasize that because there may be many solutions that might lead to the same image. X may not be unique. So in other words, there may exist many trapdoors or many this inverse function that could give us its pre-image. And actually this will play a crucial role in our security proof. Now I'll give the construction of this trapdoor. We let A bar be a random matrix in and R bar also be a random square matrix. Then this A is defined to be I'll explain what is G later. So the first observation is A times B equal to right? And well, I'll define G now. G is something looks like that. Its first row is 1, 2, 4, 8, blah blah blah, and second row is 1, 2, 4, 8, and so on and so forth. So it can be also written as identity tensor product. Oh, 1, 2, 4. And why we should care about this G? Because G have a very trivial trapdoor. If you set this A to be that G, and trapdoor is given by, I'll leave this as an exercise. G has a very trivial trapdoor. Now I'll just show you the signature scheme, and you can easily verify it works. The signature is given a message, and the signature is actually is a hash function, and G minus is defined to be the inverse function of this. What's the inverse function of this? Well, it's just the bit decomposition the bit decomposition function where you give G minus 1 is you give a vector A1 to the AN, and you output its bit decomposition. Let's say A1 is 0, 1, 0. This is a bit decomposition of A1, and this is a bit decomposition of A2. And you can easily check the correctness because A times sigma is equal to A times R is this G, so it's equals to G times G minus, and this is simply the message. And now it remains to argue its security. So first of all, I want to claim that this matrix A is still random because the lattice problem is hard only if this A is random. I want to claim A constructed in this way is random, is uniformly random. Why? This part A is random, and I claim that this multiplication is also random. The intuition is because R is random, and I is random in m times n, and you multiply it by a matrix to get a result in A areas in m times m. So this is a smaller space than this. So we have sufficient randomness to make AR also random, and this is called, formally it's called a leftover hash lemma. That basically says if you multiply by a random matrix and the result is smaller than the original random source, the output will also be random. And this G is just a constant, and random plus a constant is also random. So this A is uniformly random. And secondly, there is a trivial attack for this trivial scheme. Well, recall that the attacker can have many samples of many pairs of message and a signature. H is known to attack, message is known to attack. G is also a public, I just define here, G inverse is also public. So he actually has a system of linear equations where signature equals to R times something was public. The only unknown was this R. So after attacker have access to many signature and message pairs, he can solve this linear equation to recover the R. And know that R should be private because the one-way function holds only if the attacker doesn't have access to the trapdoor. If attacker has trapdoor, this function is no longer one-way. So R needs to be hidden from attacker all the time. And the way to so the solution to fix that is that, recall I mentioned here that this pre-image is not unique and this trapdoor is unique. Then instead of applying a G here, we can replace G by a random process or a random sampling. So this is very complex, and I'll discuss today. The basic idea is instead of applying a public fixed function, we replace it by a random sampling process that gives us the similar effect of inverse. In this way, the attacker cannot have no idea which trapdoor you use because there are many trapdoors, and they all give you the same output distribution. Okay, that's all. Thank you.